Alright, welcome to another video about how to solve moments questions. So this question has got 3 parts, but let's have a look. So a simple suspension bridge covers a narrow river, a uniform beam, 4 meters long, mass 60 kilograms, supported by vertical cables attached at a distance of 0.75 meters from each end of the beam. So the first part, find the tension in each cable when a buoy of mass 50 kilograms stands 1 meter from the end of the bridge. So let's draw a diagram. Right, we've got our uniform beam there, and we know we've got 2 cables there. There's going to be a tension in each cable, so let's say T1 is here and T2 is here. This distance 0.75 meters. And this distance is also 0.75 meters, which means that in the middle we've got 2.5 meters to add up to the total of 4 meters, and its weight, it's uniform, so its weight is going to act right in the middle. Weight is 60 g, and that distance is going to be 1.25 on each side there, because it's directly in the middle of the beam, so 2 from each end, 2 meters from each end. Add our units there. Okay, so in the first part we've got a buoy standing 1 meter from the end of the bridge. Now because this is symmetrical, it doesn't matter at all which end he stands from, so let's put him over here. So if he's standing there, we're going to have his force acting downwards, which is going to be equal to his weight, which is 50 g, and that's going to be 0.25 meters there. Not really got enough space, but you can see what it is. And we want the tension in each cable. So let's label the points of our cables A and B there to make things a bit easier, and let's start with moments about A. That will eliminate T1 because that force is acting directly through A, so it won't have a moment, or it will have a moment of 0. So let's think about what clockwise forces we have. Well, we've got the buoy's 50 g, and he's 0.25 meters away from A. The weight of the bridge will also be clockwise, going down that way, so that will be 60 g, and that's 1.25 meters away. Then T2 is going to be anti-clockwise, so we're going to have, we'll call that negative, or we'll just say it's going to be equal because we know it's not moving. So we've got T2 times 2.5, because that's 2.5 meters away from A. Now we just simply need to solve for T2, and we end up with 50 times 9.8 times 0.25 plus 60 times 9.8 times 1.25. That's going to be our total clockwise moment, and then we're just going to divide that by 2.5 to find T2. Which is, okay, let me just do that again. 50 times 9.8 times 0.25 plus 60 times 9.8 times 1.25 divided by 2.5. Okay, 343 newtons is T2. Then to find T1, let's just resolve vertically. And we know that T1 plus 343 should be equal to the downwards forces, 60g plus 50g, which will give us T1 equaling 735 newtons. Okay, so those are our 2 tensions. Now let's do part 2. Can a couple walking hand in hand cross the bridge safely without it tipping if their combined mass is 115 kilograms? Okay, so to think about whether this is possible, you need to think about at what point or points on the bridge would it be most likely to tip if they were indeed too heavy. Okay, and I think that will be at the end, because anywhere in the middle sort of it's more likely to be balanced by both of the tension forces, whereas if they stand on one end, that's more likely to tip. Okay, so let's imagine that they're standing on one end and see if when they're on the end, is that going to be safe? So we'll draw it again. We've got, most of it's the same. We've got T1 and T2 there. We've got the same distances. The weight of the bridge is still acting down in the middle there. And now we're going to say that that couple is on the end of the bridge, and it says that their weight is their mass is 115 kilograms. Their weight is 115 g. So let's think then about what happens. So if this is remaining in equilibrium, we're going to imagine that it is remaining in equilibrium and see if anything happens that doesn't seem to make sense. Now, let's take moments about A again, because if them standing there is going to cause a tip, it's most likely to be about A. So clockwise, we've got 60g times 1.25, and we've got, that's the only one clockwise. So then anti-clockwise, we've got T2 times 2.5, and this will also cause an anti-clockwise turn, so minus 115 g times 0.75, and that's going to equal 0. I see that I've done these two slightly differently, but it's all means the same thing. So we are imagining that it is, or assuming that it is going to be in equilibrium. Let's rearrange and solve this for T2. So we're going to end up with 60 g times 1.25 minus 115 g times 0.75 equals 2.5 T2. So let's see what T2 ends up equaling in this situation. So 60 times 9.8 times 1.25 minus 115 times 9.8 times 0.75. Right, so we end up with, divided by 2.5. We end up with T2 needing to equal negative 44.1. Now, the tension acting upwards here can't be negative. What this is telling us is, for that couple to stand comfortably here, there would need to be another force acting downwards over here, which means that no, they cannot walk across safely. Okay, it doesn't work. Okay, now let's move on finally to part 3. So part 3 asks, what is the mass of a person standing on the end of a bridge when the tension in one cable is 4 times that in the other cable? Okay, so let's draw our bridge again. We've got T1 here and T2 here, same distances again, it's the same bridge. We've still got the weight acting in the middle. Okay, and it says there's a person standing on the end of the bridge, so let's put them here. So their weight would be mg over here. And the tension in one cable is 4 times that in the other cable. Well, if they're standing here, this tension is going to be the greater one because that's what they are closer to. That's the kind of point that they are going to tend it to tip around. So the tension in T1 is going to be the bigger one. So we're going to say T1 equals 4T2 because we are told in the question that it's 4 times that in the other cable. Which means resolving vertically that 4T2, because that's T1, plus T2 equals 60G plus mg. So 5T2 equals 60G plus mg, which means T2 equals 12G plus 1/5 mg. Okay, and that's going to be useful later to have our T2 in terms of m. So now let's go back to moments and take moments about A again. And we're looking at clockwise first of all, so we've got 60G times 1.25. That's the only clockwise one. That's going to be equal to the anti-clockwise moments. So we've got T2 times 2.5. That one, and we've also got mg times 0.75. Now we can use this T2 over here. So 60G times 1.25 equals 12G plus 1/5 mg times 2.5 plus 0.75 mg. Okay, and now this does look a bit messy, but really we just need to solve it for m. So let's do some rearranging here. So in fact g is in every single term, so we'll cancel, which is nice. So we have 60 times 1.25, which is 75, equals 12 times 2.5 is 30, plus 1/5 of 2.5 is 1/2,